Good day, and thank you for attending this webinar on AGV system technologies and system planning. My name is Gary Koff, and I'm the president of Savant Automation in Grand Rapids, Michigan. It's a pleasure to have you attend this webinar, and I'm looking forward to providing as much information in this hour as I can. You can always contact me in the future for additional assistance. First, a little background about Savant Automation. We actually go back to the earliest days of the automatic guided vehicle business when they were called driverless vehicles. Our founding company was called Barrett Electronics. They started in 1953 with the invention of the AGV. In 1982, Mannesmann de Mag, a big German company, purchased Barrett Electronics, and in 1991, Mannesmann de Mag also purchased Rapistan Conveyor in Grand Rapids, Michigan. In 2000, Siemens purchased Mannesmann de Mag, and our name changed to Siemens Dematic. And in 2004, the AGV group at Siemens Dematic was spun off as a separate independent business, which we named Savant Automation. So we go back approximately 60 years. We've been in the AGV business that long. We've just had different names. We've done thousands of AGV systems and vehicles. Today I'd like to review several key factors in the AGV business: the market, the vehicle types, the types of navigation used on these vehicles, how these vehicles operate with respect to routing themselves through a system, through a network path, and avoiding running into each other as they operate on that path. Also, the very important safety aspects of automatic guided vehicles. Then there's the topic of system controls. How are these systems managed? How are vehicles dispatched? And how to estimate the number of vehicles required in an application. And last but not least, what everybody wants to get a feel for fairly quickly when looking at a project, how to estimate the costs of a project. So let's first begin by talking about the types of systems sold every year in North America. There are really four types of systems: the tow type systems, carrier, where the load is carried on top of a vehicle, fork, and automatic guided vehicle cart type systems, or automatic guided carts, AGCs. And as you can see, AGCs dominate over 50% of the applications done in the United States and North America every year, and the relative size of the other markets. You can also look at this in terms of the types of vehicles sold per year relative to each other. And again, the AGC types, which are lower cost, dominate the unit sales per year in North America. And likewise, the average system price is a bit different. The fork type vehicles are the most expensive types of systems, whereas the AGC types are typically the lower price type systems, and that sort of explains why there are more of those vehicles sold per year. So as you can see, AGCs are the types of vehicles that are dominating the market in terms of number of systems and units sold per year. So let's focus on these types of vehicles a little bit deeper. First, we'll look at the conventional type AGVs, which are towing, and they can run outdoors, they can run up and down ramps, they can tow loads from a couple of thousand pounds up to 50 or 100,000 pounds. So you'll find these types of systems in warehouses, distribution, some manufacturing facilities where there are long runs, those types of high volume, long distance moves. Then there are the carrier type AGVs, which carry the load on top of a vehicle. They can have lift lower decks, roller decks. They can have chain decks. You can have them in single, multiple deck configurations. These vehicles are basically self-contained and do automatic loading and unloading at pick and drop stations, conveyor stations, lift stands, and so forth. And the last type of conventional AGV is the fork type, and there are many varieties, straddle type fork trucks, counterbalanced fork trucks. There's a part of that market of fork trucks that do automatic truck loading, a fairly expensive application. Most fork type systems are in warehouses or manufacturing, stay inside the building, do floor to stand or floor to rack type loading. These are the more expensive types of AGVs. Because the automatic guided cart type systems are such a dominating market, we'll look a little bit deeper into those types of systems and learn why AGCs are so popular. First of all, it's because they can do so many different things. They can move racks with parts. Here's an application where they're moving trash bins full of dunnage. They can have powered decks, lift and lower decks. They can tow strings of carts. They can be used on assembly lines. They're also used in hospitals. So basically, this is one of the reasons why they're so dominant. They're quite versatile. They're like the Swiss Army knife of guided vehicles. They have so many possible uses because the base vehicle tends to be a standard design, and it's the cart that really makes the difference, the cart that's over the top of the vehicle, whether it's a parts rack, a shelf rack, a platform that carries pallets, or even assemblies down an assembly line. And this makes these vehicles considerably less expensive because they don't have to be built to carry heavy weight on top of them. Rather, they're towing it from underneath. They're underneath the actual platform that carries the weight. And so they're about a third to a half less costly than conventional AGVs. They're also, as I said, a very standard design. They don't have to be extensively customized or modified. It's simply the cart or the platform that they're attached to that makes each system unique, not the vehicle itself. This keeps the cost down and the engineering per system down and the complexity lower. This also makes these systems quite easy to deploy and maintain because the vehicles really are the same design for most applications, and therefore they have the highest uptime. A little look at the history of AGCs. They were not the original types of vehicles. They were really introduced in the 1990s because they were low-cost alternates or alternatives to AGVs, and they followed a magnetic tape or optical floor tape, making the installation of these systems less expensive and flexible. They originated in Japan, and initially they were employed in the Japanese transplant plants that came to the United States. They brought that technology with them and used it extensively in their plants. Ultimately, that spread out to all types of companies in the United States which make heavy use of these. The newest innovation is the tape-free AGC, which was introduced in 2010 by Savant, and it's still the only alternate to tape-guided AGCs. And it does address one of the deficiencies of an AGC, which is the tape on the floor, which gets worn or torn over time if it's in a traffic area. So this eliminates that problem, and it's resulted in some very strong sales for a tape-free product. So let's look a little bit closer at the AGC and its uses. First of all, for cart transportation. You can have your own carts, what are unique to your facility or your application. These can be shelf carts. In this picture, the vehicle services a bank of carts that have parts bins in them, and it's taking them to various assembly areas in the facility. It's supplying kits basically from a kit staging area. Dunnage transportation in a medical facility or another facility where they generate a lot of trash at different departments and have to move it to a compactor area. It's a very simple process to deliver an empty and pick up a full completely automatically. Here's a typical parts cart in an automotive application being transported by an AGC. And even in plastics, there's really no limit to the cart types that can be transported. These carts are injection molded parts in sleeves, and they're picked up at injection molding machines and taken to assembly areas or storage areas. It's basically a process of delivering an empty, picking up a full, or delivering a full and picking up an empty, depending on the process. The vehicles can easily interface with other automation. For example, an automatic storage and retrieval system. You can see the load frame is what is transported by the vehicle, and at times there's a rack on the load frame, and other times there's no rack on the load frame transported by the vehicle. And here's a video showing the tape-free vehicles, their capabilities to automatically reverse, leave a cart, pick up a cart, and it's all synchronized, integrated with other automation. Here the vehicle is backing into a station. When it gets in position, it's going to signal its arrival. An automatic storage retrieval machine will deliver loads to parked vehicles and retrieve loads from vehicles delivering racks. Destinations for the vehicles are communicated via RF, so they know where to take the racks, to what areas of the building. They also do RFID tag reading or barcode readings so they can keep track of the racks that are on board the vehicles and when and where they are delivered. Another good application for AGCs are powered decks. So here you can see a vehicle being used in a chain deck application or a roller deck application, and basically the vehicle can be configured for whatever is necessary in a given automatic load transfer application. As long as the vehicle can be underneath the powered load cart, it is pinned to that cart so it becomes one integrated unit, and it supplies power to the chain deck or roller deck or lift deck so that it is a fully automated load handling capability. Here you can see a vehicle transferring a load to a stand. Vehicles can have different deck configurations off the side. Here's another vehicle with a belt deck off the nose and tail. This vehicle handles chimney stacked loads on slip sheets, so there's sides to the vehicle. It's a belt type vehicle to handle a relatively unstable load so it doesn't tip, and a roller vehicle with a different elevation to match the customer's conveyor elevation at his machining processes. And here's that vehicle operating. It doesn't even have to be a large area that the vehicles operate in. These vehicles are very maneuverable. As you can see, it's a tight area, so the vehicle has to pull forward, then back into the load station automatically, take on a load, and take it to a destination where it will be further processed. Many of these systems are used in shuttling type applications where conveyors to link different areas would block access to the aisles, block normal traffic. And here you can see, of course, a tape-free AGC doesn't block traffic. There's no tape to be torn up if fork trucks are driving in the area, and it's completely automated. The next vehicle pulls up ready to move into the station as the first vehicle departs. Another popular use is for assembly lines. The vehicles follow each other very closely. They can be different types of operations, continuous slow speed movement on the order of maybe a foot per minute, even slower if necessary. There can be indexed movement that is synchronized. All vehicles move to the next station at the same time, or they move independent of each other. When an operator at a station is complete, he releases the vehicle, so it's an asynchronous movement. Of course, these are very flexible. The number of stations, the path, the number of vehicles can all be changed. It's much more flexible than a conveyor assembly line, a tow chain assembly line, or anything with hard automation. And the vehicles can get quite close to one another, so there can be good buffering and good service to every station. Plus, you can branch off into multiple stations in areas, or branch off into test stations along the assembly line. You can interface with robotics and do very precise stopping within a half or a quarter of an inch, or better if necessary, to interface with other precision subsystems. Another use of AGCs is for towing, simple towing. Again, these vehicles are very versatile. They can tow single or multiple carts at a time. They can even leave a string of carts in an area or pick up a string of carts and take it to a new area automatically. We have different styles of these vehicles, different capacities that can run anywhere from a couple thousand-pound capacity to well over 15,000 pound capacity in these types of vehicles. And here you can see a really nice and relatively simple way to use these vehicles in a more automated sense. The vehicle can actually drive up to a side spur where there's some carts parked. It can automatically back up, back into the lead cart. Behind the lead cart, there would be other carts or dollies hitched. The vehicle simply backs in very accurately, not using any tape to guide it on the floor. It's all following a map in its memory. And once it gets under the cart, it raises a pin. The cart then is captured by the vehicle, and the entire string of carts is therefore towed away from the line or the parking spur onto the main path and taken to a new destination. Again, the AGCs here would receive their destinations from a central dispatching controller, which would tell them where to take carts or where to pick up carts based on input-output signals from control panels on the floor or other devices or subsystems that communicate with the AGV controller. Another market for these types of vehicles would be in hospitals. The same vehicle, only in a stainless body for hospital use, can move all types of hospital carts, food, linen, supply, even surgical kits to the surgical suites. These vehicles are very efficient, and hospitals have long distances to travel and multiple floors to service, and lots of people pushing carts around. So these types of vehicles can obviously reduce manpower. That improves efficiency, but it also controls and lets the hospital know where every cart is and when it's delivered or when it's picked up in an area. The vehicles, and all these vehicles, do automatic charging so that there's very little for the operators to do to keep the system in operation every day with minimal effort. So let's look now at how these vehicles navigate around a path. Every automatic guided vehicle has to do this somehow. For the first 30 years of the AGV business, there was a wire cut in the floor, saw cut in about a ½ inch to an inch slot, a ¼ inch wide, and then backfilled, and the vehicle followed the magnetic field around the wire. Then some early tape-based technology was introduced for simpler applications, and then a real breakthrough, getting rid of the wire and the tape, was through the use of laser targets, where a rotating laser beam on a top of a vehicle sent out a laser light that bounced off of targets on walls and columns, and the vehicle would triangulate its position to a map in its memory and follow that map. Then another type of non-wire technology was introduced, which is called inertial, which eliminated the targets and the rotating laser light on top of the vehicle, and that also uses a CAD map in the vehicle's memory. So let's take a closer look at these technologies. They all work, but in some cases, one works better in a given application than another. So the laser target type technology sends out this laser beam, and it needs to see targets. So it needs line of sight. The targets are about 7 feet off the floor, so it needs line of sight to those targets. Generally has to see 3 targets all the time, otherwise the vehicle would stop or certainly slow down until it can see enough targets to guide accurately. So the targets have to be above the floor, the general size, 12 inches, 16 inches tall, 6 inches wide. They're getting smaller now. They're about 20 to 50 feet on both sides of the path. After they're installed, they have to be surveyed so their position shows up on the CAD map in the vehicle's memory. The vehicles do use distance measuring odometry in addition to the laser navigation, and their general accuracy is plus or minus an inch as they travel down the path. Then there's the tape-guided path. Of course, the weakness in that is that the tape does wear if it's in a main traffic aisle, and does get torn, and then you have to perform maintenance and patch the tape. So typically these would be done off the main aisle, which limits some of their application possibilities. And then there's the inertial technology, and to use the inertial technology, which I'm going to explain in a following slide here, you have to put a little magnet in the floor. So it's like a laser target, about 20 to 50 feet apart, but it's recessed in the floor. It's only about an inch deep and about a ½ inch diameter to 3/4 inch diameter. And after those are installed, they're surveyed like the laser targets, and then that information goes on the CAD map that the vehicle follows. They use some wheel odometry like the laser-guided vehicles, and they have the same tracking accuracy of better than an inch. So real quickly, just to get a feel for the control technology, the hardware, you have these targets here, and you have the rotating laser beam on the vehicle, sending out the light that is reflected back, and the vehicle triangulates the reflections to a map in its memory and follows that map quite accurately. In the inertial magnet versus laser target, you have these little magnets in the floor. You have this little inertial sensor onboard the vehicle. It's solid state, has no moving parts. Basically, its service life is indefinite. In the laser target type navigation technology, this is a rotating motorized laser light. It costs about anywhere from $8,000 to $10,000, and it has a service life of about 3 years. So there's definitely a periodic replacement cost associated with every vehicle in a laser-guided vehicle that does not exist in an inertial vehicle, because this is a solid-state, no moving part type guidance method. Now, looking at the tape-guided systems, the tape requires you to stick the tape to the floor, have the floor very clean. Sometimes they put a coating over the tape to try to reduce the maintenance needed. If it's a high-traffic area, they have to cut a slot in the floor and put a magnetic rod that's about a 1/4 inch by a 1/2 inch deep, and it's a flexible rod, but you do have to cut the floor and put the rod in there to avoid the problems of tearing up a tape or wear and tear on a tape. And the vehicle follows the tape, and basically the controller on is solid state that senses the tape, so it normally does not have a replacement issue. You have other things you have to put in, codes in the floor done with other tape or RFID tags or embedded tags, so that as the vehicle drives along, it knows where it is, whether to blow its horn or it's at a certain station. That is picked up by reading the information in these tags. In the virtual path, laser, or inertial vehicle type systems, there are no real codes in the floor normally. The vehicle has that in its memory. Here's the inertial sensor elements. Here's the little magnet that would go in the floor. Here's the solid state inertial sensor, which is in a sealed box on the vehicle. Does not require any maintenance or service or calibration. People understand the idea of laser bouncing off of targets, but they don't really understand the inertial navigation principle. So basically, to explain it, think of the inertial sensor as a device that is like a compass. It wants to point north all the time. And the vehicle follows the map in its memory, and basically what it's doing is it's using the inertial sensor that always wants to provide a reference heading, for example, north, and comparing that to the vehicle's heading, which does change as it goes through the path, which is represented by the green arrow. So basically the vehicle is measuring the angle between the red arrow and the green arrow, and it is also measuring distance traveled and just using geometry to plot its position very accurately to the map in its memory. The inertial sensor is the same type of sensor that's used in cruise missiles to fly them through a window 500 miles away. They're used in stability control systems in cars to sense skidding of the vehicle and provide information to the car's computers to control the braking and acceleration of the vehicle so that the skid can be minimized. The laser type of vehicle here, you can see what it's doing. It's driving down a path but looking at targets, and if you have an open area, that works really fine. If you have a congested area, line of sight could be an issue. Targets could be blocked by racks or pallets, and they could be exposed to damage. So you have to be aware of this when you're looking at your application, because you may lose storage positions. You may have to move these loads to have line of sight to these targets. In this application here, you can see that these are inertial guided vehicles. There are no targets here. If there were, then these loads on this wall would have to be removed, and there would be issues putting targets on the other side of the aisle because forklifts access these pallets and could damage those targets. But with inertial technology, that's not even a factor or a consideration. So basically, the path in the inertial or laser technology is developed in a CAD layout, and the targets or the magnets are located on the path the vehicle follows. Then that is downloaded to the vehicles in the system, so they now know the new map regardless of the vehicle type. And there are tools that are available to do this. We offer a technology that makes it possible for the user to change and modify his paths and his system. Here, moving a station from one location to another, or changing a function from stop waiting for an operator to stop automatically unload. You can do all of this on your PC screen and download it to the vehicle. You can even simulate the motion of the vehicles and see if they're going to perform their traffic control and their routing and their station destination functions properly before you ever put it into the vehicles on the floor. So this technology is getting better every day to let users really make their own changes and optimize the system to their needs. So let's look at another function of the AGV system, which is how do these vehicles find their way from one station to another. In this case, there could be multiple ways to get from Station 1 to Station 7. There are two types of architectures. There's the vehicle we call a smart vehicle. It makes all its routing decisions itself. And there's a smart central architecture where there's a central controller that directs the vehicles through all the branches in the path to its final destination. So here you can see there are literally 4 different ways to get from Station 1 to Station 7, and there has to be logic in the system that optimizes which way is chosen by a vehicle. Now basically in a smart vehicle type system, the vehicle makes its decision. If it knows it's got to go to a certain station, it knows the shortest route to that station and makes those decisions by itself. There is no central controller. In the other type of architecture, the smart central, there's a central controller talking to the vehicles, and at each branch it's telling the vehicles whether to turn right or turn left in order to take the correct route to its destination. Traffic control, when you have multiple vehicles, is a very important function. Basically, you can have different ways of handling this. You can have long straight areas where there's passive separation between vehicles. This typically relies on a sensor on the front of the AGV or some kind of communication between vehicles to allow them to keep a certain distance apart. There's another type of traffic control used in systems, particularly when the path has branches and intersections, and that's a positive separation. These are areas where the passive type sensors wouldn't work because there's too many path possibilities, and the sensors can't handle all those different possibilities. It's generally necessary at intersections, path merges, and turns, and it's based on having certain fixed zone lengths. So when you have vehicles very close to each other, you have them physically separated by a positive distance, not by passive sensors. And this is typically how the two of these things work. You could have a vehicle that is stopped on the path, which is the red vehicle. Another vehicle comes up, senses it, and slows down and stops before running into the lead vehicle. The lead vehicle moves ahead, and automatically the trailing vehicle can move forward. If the lead vehicle stops at station 12, then the trailing vehicle would wait behind it. This works fine if there's no intersections in the area or turns. Now when the lead vehicle approaches an intersection, the positive separation technology takes over. The green vehicle is entering the intersection before the red vehicle, so there's a communication that takes place, and the red vehicle has to wait until the green vehicle clears the area, and then the red vehicle is allowed to move forward. And then the same thing happens with the yellow vehicle. He waits until he gets a positive signal or communication the intersection is clear. So again, in these two, this traffic control is done in two different ways depending on if it's a smart vehicle architecture. The vehicles literally talk to each other so they don't run into each other at intersections or around turns. Or if it's a smart central control system, you have this central controller which tells the vehicles wait, go, and so forth at all these control points. Again, if you have a central controller and it fails, either in the routing function of a central controller or traffic control function, then all the vehicles would stop. In the smart vehicle architecture, it's distributed intelligence, so it only affects the given vehicle that can't do its traffic control or routing. And you can't have a catastrophic system shutdown affecting all vehicles. Safety is a very important aspect of AGV systems. Today, almost all vehicles are equipped with a laser bumper. It's a safety-rated device. It has multiple zones. You can configure the shape and pattern of coverage and depth of coverage. So they're programmable, and they provide excellent safety in front or on the side or in the rear of the vehicle, depending on the need. This is the typical type of situation that occurs. Here, a person is literally walking in front of a vehicle, not paying attention, and if your volume is on, you can hear the vehicle's actually talking. So the vehicle, using its laser sensor, would stop without colliding with an object or without causing injury. And when the object is out of the way, the vehicle can automatically restart. There are various other safety measures that can be taken. You can control the speed of the vehicle in an area. You can have lights on board the vehicle, external, that are triggered when a vehicle enters an area. You can have audible and voice being used You have, of course, the laser bumpers. Some still use a physical bumper in front of the vehicle. Certainly if the vehicle strays off path by a few inches, it does shut down automatically. It doesn't continue to run, so that's a fail-safe. There are interlocks with other automation if you're going up elevators or interfacing with conveyor and the load hasn't transferred all the way on or off the vehicle. There are interlocks to prevent the vehicle from leaving until the transfer is complete. You can tie into fire alarm systems. You can have turn signals on vehicles. A lot of possible things you can employ. Systems are important. In every smart vehicle system, you have a keypad on the vehicle. You can use it for just general information, what the vehicle's doing, where it's going. You can obviously use it for diagnostics and troubleshoot the vehicle. And you can also use it for dispatching the vehicle. In many systems, an operator would just punch in the destinations on the keypad. He can put in a number of them and send the vehicle to any sequence in any order he wants. And so these types of control panels are on the vehicles. When you want to automatically dispatch vehicles, automatically call them to stations, there is another level necessary, which would be called the AGV management level. So all systems have the AGV control level, and some systems have a higher level for remote control. And again, it depends on the architecture how this is achieved. But basically, you have in both system types the virtual path. Most laser-guided systems would employ this form of central control, so there'd be the laser targets, and you'd have RF to the vehicles. Then you'd have a AGV controller to handle the traffic control and routing decisions for the vehicles as we covered earlier. And above that, you can have the AGV management system with load sensors, barcode scanners, other devices, PLC networks, interfacing with the AGV control system to call for vehicles and to send vehicles to certain destinations. And then you can have the customer's computer level if you want to report pick up and drop off information or track loads. In the smart vehicle, you have the same basic architecture down here, the RF between the base station and the vehicles. You also have the RF between the vehicles because in this level they do their traffic control and their routing logic without a central controller. So there is no central controller as there is in the Smart Central controller for the traffic control and routing. But you still have the management level if you want to do automatic calling and dispatching of AGVs. And then you have the customer facility level if you want to provide him with load move information or take from to information from his level and have the vehicles receive. Most AGV systems do some form of automatic charging, either opportunity charging or managed charging. Both are done with the same hardware. The vehicles have a pair of copper pins or contacts underneath the vehicle that make contact with a plate, either mounted to the surface of the floor or recessed in the floor, that has two copper strips in the plate which are connected to a charger off to the side of the path. The copper plate and or the wires to the charger can be recessed in the floor. The vehicle would pull up and stop over the charge plate, make contact with the copper strips, and the voltage then is sensed by the charger, which automatically turns on. When the vehicle finishes charging or is dispatched to a new location and leaves the charge plate, the charger will automatically turn off. So it's completely safe. Fleet sizing is an important consideration that depends on how the system is going to operate. Most systems do not require an expensive simulation to determine how to optimize the system or optimize the number of vehicles in the system. These simulations cost between $30,000 and $50,000 and are mostly unnecessary for the vast majority of applications. Instead, there is a tool or a spreadsheet type solution where parameters are input for the equipment, the speeds, the load transfer times, certain operational assumptions, battery charge factors, inefficiency factors, deadhead time. And these sheets, which have been developed, these calculations over time, then compute the time for AGVs to transfer loads or transport loads to different destinations in the system to meet the throughput requirements or the operational requirements. And by doing that, the result is an estimated number of vehicles required. And generally, these are pretty accurate, within 10%. And if further analysis is needed, then simulation can be performed. Determining a budget price for an AGV or AGC system opportunity should be done early in a project. The system can be reconcepted so that the pricing for the functionality required can be adjusted into an acceptable payback range. In a single vehicle system, no traffic control is required, and the budget price range is fairly easy to determine because these systems typically involve less complexity of the control system. So you can see here that the automatic guided cart type product is generally less expensive, followed by the conventional tow and carrier and then fork system within a price range of about 15%, plus or minus. I've given you some budget numbers to work with. Then when you get into quantities of vehicles, such as 5 here shown, you need a traffic control system, and generally these systems would include more complexity in the control system for automatic load transfer or remote dispatching type controls. Again, the same price range variation is involved, with AGC type vehicles systems being less expensive. The price range within 15% either way is shown in this table and is generally applicable to most applications. And then when you get into 10 vehicles, more quantity, you see a leveling off of the system costs because it's amortized over more vehicles. We have these tools available, and we certainly can do some quick budgeting, based on concepts we would develop with users, and that would allow them to see if they can justify a given application or how to shape the solution into the right justification payback range. AGV and AGC systems are now a widely accepted material handling technology used in all industries. I want to thank everybody for their participation in this webinar. I hope this information has been helpful to you. I've provided some additional resources at our website below for you to access. We look forward to helping you with any opportunities you may have in the future. Please do not hesitate to contact us. Now I have a few minutes for some questions and answers.